Okay. Uh, Dr. Steven Gough-Kelly is an astrophysicist researcher working at the University of Central Lancashire, studying galaxies, including our home, the Milky Way. In addition to his research, he has given public lectures, taught physics, and developed workshops for all ages, aiming to pass on knowledge through the curiosity of space. So can you join with me in giving Dr. Steven Gough-Kelly a big thanks for Swinton welcome. Welcome, Steve.
So good evening, everyone. Everyone hearing me okay?
Yes, thank you.
Yes.
Thank you. I'll keep my camera on for as long as possible. If we start to have any connections issues, I may turn it off. But thank you for that introduction. And apologies for the slightly kind of generalized title that you may have kind of heard. But the talk I'm hoping to give tonight is Galaxies with the Next Generation of Simulations and Great Observatories. So a big thank you to Roy Grumman for reaching out to me, inviting me to talk to you all. I'm really appreciative of you tuning in tonight, both in person. I'm sorry I couldn't be there, but it's great to see that you have a good online following as well. So just very briefly about me, I've just finished a PhD in galaxy dynamics at the Jeremiah Horrocks Institute, which is part of the University of Central Lancashire. I'm a fellow of the Royal Astronomical Society and a junior associate of LSST UK. I'll touch upon that in a little bit. And I'm a member of the N-Body Shop, which again, I'll touch upon in a little while. Now, Jeremiah Horrocks is the name of our institute. It's a historical name. He was famous in the 17th century. He accurately predicted and then observed a second transit of Venus, where during that period they thought they were occurring only once every 100 years or so. And he was one of the first to show that actually they appear in pairs about 8 years apart. And him and his friend William Crabtree in Manchester observed a transit of Venus. He was also one of the few during this period to try and estimate the size of the solar system, and actually his predictions came within orders of magnitude closer to the actual accepted true values that we have today. And even Sir Isaac Newton acknowledges Jeremiah Horrocks' work in Principia. So he's actually one of lost heroes, because actually he died at the age of 22, quite tragically. No one knows what happened to him, but he only made it to 22. And he was already making such vast discoveries so young. Imagine if he'd had lived as old as Newton did and made his contributions to society. So that's why our institute bears his name. At the University of Central Lancashire, we have an observatory site called Alston Observatory, where we have a couple of interesting telescopes, as well as a teaching building with a planetarium involved. So we do a lot of outreach and public engagement, but we also do undergraduate research and some serious postgraduate research out at the site as well. Won't take you all the way through this poster, but this is just a quick poster of what we have here. We have the Moses Holden telescope, which is a 0.7 meter CDK telescope with some very nice imaging capabilities. We also have the Wilfred Hall telescope. It's a 15-inch Grubb refractor, which unfortunately is no longer operational, but it is now a museum exhibition showing those kind of historic telescopes, but it's still a very large and impressive telescope. We have the teaching building, which has a planetarium inside, as I mentioned. And then the newest addition to the site is a wide field telescope. So both the Moses Holden and this new wide field telescope are both plane wave instruments, but the wide field telescope, I've forgotten the field of view. I think it's about a degree field of view. But it's one of the first of its telescopes in the UK. Plane waves is in the US. So this is one of the first ones to make it into Europe and into Britain, and it will be doing some wide field surveying. If you're interested about the observatory, there's a website for it, and you can potentially go as a society as a tour, and you can learn more about it there. Moses Holden is another historical figure. He was one of the founders of the university, the original institute that became the university. The Holden name has kind of lived through to the present day, because we've named two telescopes, one after the Moses Holden and one after Isabella Holden, which was his wife. And then Patrick Holden, which is a great descendant of Moses Holden, also funds the Moses Holden Studentship, which also funded my PhD studies. So with great thanks to Patrick Holden, I'm here today to be able to talk to you about some astrophysics. So that's a little bit of background. You can see the site here in Lancashire. We are no stranger to clouds ourselves, but it is still a very fantastic site when we do get those few days of clear skies. Here's an image I managed to take out there one night. The Pleiades was rising this evening, so we got some great observing in. But you can see just in the corner there, those clouds are looming and moving very quickly. And so, yes, Lancashire astronomy is challenging, but a lot has happened there over the years. So I thought I'd start talking about galaxies with one of my own images of our own galaxy. This is at Alston again. It's not particularly the prettiest, it's not the best. I'm not claiming to be an astrophotographer. I just took my DSLR out to the site and left it on the ground while we were doing some actual observing with the telescopes. And I managed to get this. Now, some of you with keen eyes, and potentially it may come through just about on your projector, but vertically through this image, you can see the dust lane of the Milky Way. Near the dead center here, you can see the double cluster. So this is my attempt of trying to capture the Milky Way, half by accident. If you were up in a very nice top of a mountain in Chile, and you had a better camera and a bit more time than I did to get a nice picture out, this potentially would be what you would see. And you've got the band of the Milky Way going across the sky here. The Milky Way name getting its name, of course, from Greek words for milk in the sky, and galaxis, again, being this kind of milky origin in its naming. Well, this is our view of our galaxy. Now, also in this image, you can see this slight smudge, and that's being nice there. It is quite smudgy, and it's very poor attempt, but this was completely by accident. I just set my camera up and managed to take this image. Now, these kind of milky structures in the sky also gained another name, which was nebulas. And some of the first objects that we started to observe in the sky that weren't stars, we started to call these nebula. Now, some of them had particular structures, which in some cases were these spiral patterns, and these became the spiral nebula. This is from an old textbook that I own, I think from the 50s or 60s, and it still lists these objects as spiral nebula. And they refer to them as nebulas because our view of the universe wasn't particularly complete. We thought, actually, everything is quite close by to us. We're in the Milky Way, and everything is inside. So these spiral nebulas are just nebulas, another part of the Milky Way galaxy that we're in. It wasn't until more recently that we started to realize that these structures were actually external to us. And it's understandable. As we had early technologies, early telescopes, we had our eyes, we had very basic glass optics. These objects did appear very murky, very nebulous, and not particularly too detailed. And we didn't quite resolve them well enough to understand what they truly are. As we started to improve our technology, we saw more and more detail, that actually these kind of dust lanes also had knots in them that were brighter. And these dark patches were dust obscuring what we were seeing. And eventually, when we get to modern day telescopes, we start to see the really detailed, fine structure of these objects. Some of these objects today still hold their kind of heritage in their naming convention. So Messier 81 still gets referred to as Bose Nebula, even though we now understand that it's a galaxy. So one of the pioneers that kind of led this charge of us understanding what galaxies are in terms of how far away they are and what that means for the structure of the universe was Edwin Hubble. Now, Edwin Hubble's name is going to come up in a few times because his legacy in naming and his work has survived through to modern astronomy. But he used some of the biggest telescopes of his time to study these objects and to truly figure out how far away they are and what that means in terms of the structure of our universe. So going back to the image that I took, this again is the galactic equator that was going through the center of the image. I've highlighted this smudge here, and then there's an even fainter smudge slightly further down that I've expanded. And again, the expansion doesn't really tell us much more, but you can see there's a bright central bit in the center, and the smudge kind of goes around it like that. This one is just a change in color. And if you weren't knowing to look for it, you may just think that that's something on the sensor. That's something that I've kind of messed up in terms of editing. It looks very peculiar. But actually, when I compare these, when we look at sky atlases and we take some nicer images using the telescopes at the university, these two images were taken using the Moses Holden telescope, the big 0.7 meter. We can see that these are both what would be referred to as nebulas, but we know as galaxies. This is Andromeda, and this is the Triangulum galaxy. So again, much better pictures than what I took with my DSLR. So Hubble's name's going to come up again because we named a telescope after him, the Hubble Space Telescope. And this was a $2 billion NASA project where we launched a telescope up into space. And then it was somebody's crazy idea to point this very expensive telescope at a patch of the sky that had effectively nothing in it. They pointed other telescopes in that direction and thought, oh, that's quite a bit of barren sky. And they thought nothing would be there. But somebody managed to convince NASA to point this very expensive machine at a patch of sky that effectively had nothing in it. And this is the image that it took. And this started to revolutionize our understanding of the scale and the scope of the universe. Because in a patch of sky that we thought contained not really much at all, we found all these galaxies. Each one of these points of light in this image, far from a few, are galaxies. And they're galaxies that are beyond the Milky Way. They're very far away. In this image, there's only a handful. There is a couple of stars. You can see this point of light here, which has a nice cross on it. And there's another one up here. These are nearby bright stars, and they get this cross from the optics of the Hubble telescope. Everything else that we see in the background, these spirally shapes, the different colors, the spherical ones, all of those are galaxies. Now, in the modern era, we have JWST, which is like a successor to Hubble, but it's different, and I'll get on to how Hubble Space Telescope and JWST are slightly different. But JWST took this image of a similar patch of sky where we expect to find not a lot, but instead we find an entire zoo of galaxies. Now, I'll teach you a small trick if you want to know the difference between a Hubble image and a JWST image. The Hubble images have a nice cross. JWST, because of its hexagonal mirrors, you get this nice 6-pointed star patterns. So that's how you can tell the difference between Hubble and JWST images. But in this as well, it just reaffirms the diversity of what galaxies look like. So Hubble had another legacy that came out of his research, and that was a classification scheme for these galaxies. We were trying to group these galaxies into similar patterns, and this is what he came up with. So we start off over on the left, and we've got these E0 to E7s. These are what we call ellipticals. So they're usually quite spherical in shape or kind of rugby ball shaped. They're slightly elongated, but they're usually quite diffuse and just quite puffy. They're just quite round. No particular substructure in them. They're the ellipticals. On the right-hand side, we have the spiral galaxies. So these are usually disc-like, and they have these dust lanes and these spiral wheel patterns, and they're split up into two subgroups. We've got the top run, which are just the spirals. They just have spirals, and they come to a point in the center. And on the bottom rung, we've got spirals, but they have a structure in the center that we call the bar. Bars are very fascinating to my research. They're really cool structures, and we'll get into that a little later on. But those are the distinctions that Hubble chose. Now you can see along the spiral branches, you've got SA, B, and C, or SB, which is spiral barred, and then A, B, and C again. The A, B, and C just describe how tightly wound those spirals are and how big the central region is. This central region I'll get onto as well. The Milky Way, for context, sits along this branch. So there's Milky Way's got a bar in its center. So it's an SB galaxy, but then it's somewhere between a B and a C. So its usual classification is an SB-BC. So it sits somewhere in the middle of here. So we've got some loosely wound spirals, and we've got a bar in our center. That's where the Milky Way sits. Now, when this started to be introduced, this kind of classification scheme, astronomers started to refer to these ellipticals as early type galaxies and these spirals as late type galaxies. They thought that these spirals, because they may take longer to evolve, they must appear later in the universe. So we started to tag these names onto it. So we have early and late types. And in research, they're used quite a lot. And some people started to mistake that as actually this might mean that this is how galaxies evolve, that we start elliptical and we end up as spirals. And that would be not so correct. In fact, what is closer to being correct is actually the opposite. Okay. So even though galaxy evolution probably looks towards the other direction, astronomers, because we're quite stubborn and we don't particularly like change sometimes, we still use the terms early and late. Okay. They've just kind of stuck around as naming conventions, but they do not reflect how we kind of understand how galaxies evolve. Just to give you another insight into kind of how diverse galaxies are, this is almost like the galaxy zoo as seen by another space telescope called Spitzer. So this is the Spitzer Infrared Nearby Galaxies Survey, or SINGS. If there's another thing that I can teach you about, especially professional astronomers, is that we are terrible at naming things and we love acronyms, but we tend to work from a nice word and work backwards with an acronym, and we try and make it fit. But this is the SINGS survey. And here is the Hubble classification scheme with images from Spitzer. And again, you can see the diversity as we go from all these different spirals with some of the bars with different bulges. We've got a whole bunch of irregulars, which are ones that don't fit into each of these kind of categories. But as we start to develop more modern telescope technologies, we really get a real insight into the diversity and the different structures that we can see inside these galaxies. Now, one of the more modern ways that we start to classify things, some of you may be familiar with these projects. If you're not, I would highly recommend looking up at Zooniverse. But the project started as Galaxy Zoo. This was a citizen science project where they took images from the Sloan Digital Sky Survey, which is a different telescope, and then they posted them all on a website, and you could log on as a citizen scientist and classify galaxies. So you'll get an image of a galaxy and you can say, is it an elliptical? Has it got spirals? What do the spirals look like? So are there any other features? In each iteration of the project, the different classifications got more and more complex, but it actually became one of the most valuable resources in studying galaxy morphology, or how galaxies look. And this spawned the Zooniverse project, which is a citizen science platform which anyone can sign up to and do classifications of different things. But the Galaxy Zoo project is still going on, and you can still classify galaxies. And we're still finding more and more new insights into the weird and peculiar galaxies that we see out in the universe. Now, in the most current iterations, we now have a combination of citizen science and machine learning techniques. So the citizen science will do a lot of the hard lifting, where they'll go in and look and find detail of some of these objects. That will teach the machine learning algorithms to spot all the obvious cases. But then what it can also do is flag some of the weird cases and send that back to the citizen scientists to have a closer look. So machine learning is really good at spotting all the obvious cases, all the galaxies that we've kind of seen before. But actually, people's eyes do a really good job of finding all the weird and niche galaxies out there. So if you haven't seen Zooniverse before, I'd recommend going and having a look. So to talk about galaxy formation and galaxy evolution and how we get back to the kind of current image that we see of the universe, we're going to very quickly go right back to the beginning. So our universe starts as a singularity, as a very, very tiny point in space. And the very, very tiny world is dictated by quantum mechanics. So in the physics of the very small, we're dominated by quantum mechanics. So these quantum things jumping in and out of existence, fluctuating. And then what happens is, as the universe expands very rapidly from a tiny point, these quantum fluctuations, these very, very tiny little changes in the tiny universe get exploded up into the biggest scales. And what we get is the afterglow of the inflation, or the Big Bang, which we know as the cosmic microwave background. So these are the tiny fluctuations in heat that we see in the residual of the universe, all the way around us. And these are just tiny fluctuations in quantum mechanics that are blown up to the cosmic scale. Now, these fluctuations then start to embed and seed the universe, because where we've got hotter temperatures and colder temperatures changes the density of where we find matter. And where we've got over densities of matter, that's where we start to find galaxies and galaxy clusters. And in these lower density regions, we find big voids where there's not really much galaxies or anything going on at all. So, sorry, I'm going to get slightly ahead of myself there. So when the universe was expanding, the universe was still very, very hot. When matter gets really, really hot, it effectively turns back into energy. If we think from Einstein's equation, E equals mc squared, when we have matter and it's heated up to very, very high temperatures, which the universe was, it effectively becomes energy and light. So when the universe is too hot, matter can't come together and form gas. It can't form any elements. It's just too hot. So everything's broken apart and it's effectively existing as energy. Dark matter, on the other hand, which is this kind of theorized substance which kind of holds the universe together, doesn't interact with light. It doesn't care about light. So it can still collapse under gravity. So in the early universe, when everything's too hot, atoms can't form, but dark matter can start to clump together. It clumps together in these kind of structures. We call this the cosmic web. So it looks a little bit like a brain neurons. This is one of the kind of fascinating things about science, is that actually the universe looks almost like the internal structure of our brain. But what happens is dark matter starts to collapse along these filaments. So we get these long spindly structures, and then where spindly structures start to come together, we get these knots of density where there's like high density dark matter, and it creates this kind of structure. This is actually from a simulation of the early universe called EAGLE, so the Evolution and Assembly of Galaxies and Their Environments. Again, astronomers are terrible with acronyms with a random L in the middle, but we wanted it to spell EAGLE, so that's how it's come about. But this is a simulation of how the early universe looks like, with the dark matter starting to collapse into these filaments. So because the dark matter has already laid the groundwork of gravity, it's formed these structures. By the time the universe is cooled enough for gas to be able to form, the atoms to be able to form, they already have this structure to fall down with gravity. So the dark matter is already pulling the gas together along these filaments. And when it starts to do that and funnel this gas down these filaments, we get gas collecting up, and then we start to form galaxies in these knot regions. Now, when gas starts to fall inwards and collapse in on itself, it starts to rotate a little bit. And when you get a little bit of rotation, as you start to collapse further and further, you get more and more rotation. And when things start to rotate, they start to form disks. The universe likes to form disks. So whenever you've got something collapsing down, it starts to form flat structures. It's the same thing with why the Earth is not exactly spherical. Because the Earth is spinning, it doesn't want to be spherical. It wants to squash down into a flat disk. So if the Earth was spinning fast enough, we'd become a disk slowly as well. But we're not spinning fast enough, so we just appear as a oblate sphere. We squish out a little bit. Now, as gas starts to form down these filaments and squash and spin, if it squashes far enough, the gas turns into stars. So when you squash gas hard enough, you start to get fusion happening, and that's where you get star formation. That's where our stars are born, and that happens a lot in the galaxies. So this is the same principle as an ice skater pulling their arms in, and they start to spin faster. So an ice skater who's spinning slowly, when they pull their arms in and their body tucked up, they spin faster and faster and faster. As gas collapses down, it starts to spin faster and faster and faster, and it flattens out into a disk, which we now see as spiral galaxies. So in the early universe, we have a bunch of spiral galaxies starting to form. So where do all these ellipticals come from? Well, if you've got many spiral galaxies being in close proximity and they start to interact with each other and they start to merge together, this mixing process is quite violent, and actually we don't get these disks anymore. What we get is some starbursting happening, where we get these beautiful galaxies which are exploding in star formation because all the gas of two different galaxies are colliding together now. And it starts to form this irregular shape. But once it all starts to settle down, we're left with just an elliptical galaxy, which is no longer forming any stars, which is why we don't get these beautiful blues and these pinks that we observe in these spiral galaxies. And that's what's left behind. So the universe likes to form spiral galaxies, but when they start to interact with their neighbors, they start to mix together and we end up with these ellipticals. So thinking about this classification scheme and kind of how we think about formation and evolution, we tend to start with some spirals, and then when they start to interact and merge together, that's where we start to form all these ellipses. So it's not as simple as just a straight line between this classification scheme. Galaxy evolution is a bit of a messy process, and it can take various routes. But this classification scheme is still very good for our understanding of breaking down the different types of galaxies that we see. So, where do myself and other people who work in my field on simulations come into this? Because I've shown you plenty of pictures. I've shown you this is how we think about the understanding of evolution of galaxies, but how are we shown this kind of directly through simulation? Now, to be able to do that, we need to start thinking about the laws of physics that govern the universe, and one of them being gravity. Now, if we think about Newtonian gravity, famous for the apple falling on his head, and we think about the gravity between two objects, this is relatively trivial to kind of calculate. So the force of one object on another object, Newton described in his force of gravity, and it's to do with the mass of the two objects. And the equation he derived for that is relatively simple when you have two objects of a given mass. We can calculate that directly between them. We can calculate the motion of one object around another object relatively simply. The problem becomes is when we add a third object, because now we're trying to solve the positions and the velocities of three different objects and the forces and all those three different things all at the same time. And this becomes known as the three-body problem, and it's not solvable analytically. Okay, meaning that you can just write one simple equation and it describes the motion beautifully, and all systems go. It really doesn't work for three bodies. The only really way we can get around this is if we pretend that that third object has a teeny tiny mass that doesn't exert any gravity on the other two. So if you can imagine like an asteroid going around the planet, then you could probably solve for that because its mass is so tiny compared to the planet and the sun. But if our solar system is made up of multiple planets, which it is, made up of moons and planets as well as the sun, and then if we're thinking on the scale of a galaxy where you've got multiple stars with multiple planets around it, it starts to become a very messy problem. And we could move to something which is called n-body problems, which n being any number of bodies. So we can't solve this analytically using a very nice equation, but we can make approximations, so we can do estimates, which gets us very, very close to the answer, but not a very true exact mathematical solution. But one of the first kind of n-body solutions, sorry, this is my picture of the solar system with my dog flying through it, to describe this point. One of the first persons to kind of explore n-body simulations, or bigger than kind of two-body problems, is Erich Hornberg in 1941. And he used a very clever trick. The force of gravity varies by distance as what we call an inverse square law, which is as you double the distance between two objects, the force of gravity is divided by 4. It's a fourth the strength. Light intensity also follows the same relationship. So as you double the distance away from a torch, the intensity of that light is divided by 4. So he devised an experiment where he laid out a whole bunch of light bulbs out in his lab. And then he used a light meter, so just to measure the intensity of light, and he could place it in different places around his lab. And he calculated the force of gravity of each of these points on each of the rest, did some calculations, and was able to move the lamps around based on what the forces of gravity were, and then do it all again, move his light meter around, take the measurements again, move his light bulbs. And what he did was, this was for two galaxies very close by interacting. So you can see their motion. And when you end up here, is you can see each of these two distinct galaxies with one of their spiral arms coming out, and this kind of interaction zone in between the two of them there. Somebody in the 2010s reproduced this experiment in a university in Finland for a master's thesis. And I think this is a really beautiful kind of depiction of the original experiment, where you can see all the wires going to each of these individual bulbs, and you can see the same processes stepping through until we start to see that same image. And this experiment did a remarkable job of computationally trying to show how the gravity interacts between two galaxies. I think this is really kind of a beautiful image between what we can observe to what he predicted with just light bulbs and a light meter and a basic understanding of gravity, from effectively Newtonian gravity. Nowadays, we're now dealing with orders of millions of bodies. We've now started to introduce new physics as well, because we have gas in galaxies, and gas is a fluid. So we have the physics of fluids and how they interact with temperature and pressure, as well as under gravity. In even more modern simulations, we now have to include things like magnetic fields. Bonus points if you know which sci-fi show I'm referencing with those images there. But the latest iterations of simulations also include magnetic fields, where gas is a plasma and it flows along magnetic field lines. They're being introduced to these simulations as well. And when we combine all this together, we teach the computer all this physics that we know: gravity, fluids, magnetic fields. What we get out the other side is some really incredible simulations of what look like real-life galaxies. Now, the beauty of it being a simulation is if we have access to all the information about individual stars, about how the gas flows through the galaxies, we can turn back the clock, we can turn forward the clock, we can figure out how each galaxy went through each process to make it look like the way it did towards the end of a simulation. Now, even with modern computing, these things take a lot of power and a lot of memory, a lot of computing energy to do this. And if we're doing it for a single galaxy at a time, it's a very long and iterative process. You can still learn lots about galaxies from individual simulations like this, and they're still vital to our research. But this is just kind of one simulation, and we get one galaxy out at the other side. So to use another sci-fi analogy, apology, I've got a couple of these. This could be seen as kind of like the original series of simulations. We're looking at kind of like the first iterations of simulations going on. We're now entering what I would essentially call the next generation of simulations. Now, the reason we're calling this is because this is inspired by a particular simulation suite that I've been using in my research, and this is called the Illustris TNG simulation, or the Illustris Next Generation. Now, Illustris TNG is a set of 3 simulations of an entire chunk of the universe. Now, we still can't simulate the entire universe, it's just too big, but we're trying to simulate big chunks of it at a time. Now, when it comes to computing, there's a trade-off between how big of a chunk of the universe you want to simulate, or to what kind of resolution, or to how much detail you need about the simulation to study. And so this is why there's a suite of 3 of them, because one of them is the biggest, but it has the least amount of detail in terms of individual galaxies, but we can see a big chunk of the universe. But on the other side, we've got TNG 50, which is a smaller volume of the universe, but it's in very high detail. And we focus mainly on TNG 50 because my research is focused more on the internal evolution of galaxies. So we really need that fine detail on the individual galaxy level. But unfortunately, we only have a smaller sample. But we still end up with hundreds and or thousands of galaxies to be able to study in this simulation. So it's still a big chunk of the universe. So for the same simulation that we've run on a very massive supercomputer, we've got to study thousands of galaxies all in one go. Here's just one example of them. On the top left, you've got the real image of M104. You may know it as the Sombrero Galaxy. And then the rest of the panels are 5 different TNG 50 galaxies. So these are all simulated galaxies that look very similar to it. Now, because TNG is reproducing galaxies that look realistic, that look like galaxies we observe, studying the simulation will tell us what the Sombrero Galaxy's history was like, what environment it was in, and the physics that went into creating that galaxy, and what makes it look the way that it does. So starting to go towards my research, I'm really interested in the centers of galaxies. So just to do a quick comparison, the Sombrero Galaxy again, and then we've got this other galaxy here, NGC 4710. And I've got some pictures here that describe the central regions. So in Sombrero Galaxy, if we look towards the center where it's very bright, we see the central region is quite round and diffuse. It's quite spherical. So you could describe it as some level of kind of walnut shape. NGC 4710, I hope you kind of can see enough detail on the projector, but you can see these got 4 spikes out into the corner. And if we think about the kind of middle section here, as we go out to either side, it's kind of peanut shaped. So it's pinched in the middle and goes out to the edges. So hopefully you can see that kind of 4 spike there. And we do call these peanut shaped bulges. The reason we call them bulges is because if they're in a disk galaxy, they stick out the plane, they bulge out of the plane of the disk. So astronomers, unimaginatively, we call them bulges, just describing them how they are. And these differences in the shapes of these bulges give us an indication of what these galaxies go through and what structures are in the galaxy. And I'm going to focus mainly on these peanut-shaped ones. Now, hopefully this video comes through. If it's a little bit jerky, don't worry, because it'll be the final frame that I'm most interested in. But this is a simulation of a galaxy, and we're looking at it slightly edge on. And you have that bar structure that was in the center, and it rotates round. And this bar structure kind of acts like a fire hose when you're pumping water through it. Because when you've got a hose and you pump water through it and you leave the end kind of untethered down, it starts to wobble, it starts to bend, and it starts to shake. And this bar starts to bend out of the plane of the galaxy and form this kind of pointed X shape. So this happens only in barred spiral galaxies. And the Milky Way is one of those, which is why we're interested in studying them. So what we did is we hunted through TNG 50, through these thousands of galaxies, to try and hunt for the bars and these kind of BP-shaped bulges, or these boxy peanut-shaped bulges. We defined some metrics. So this is the bar strength against time. So as the simulation is evolving, as we're watching these galaxies and measuring at each time what the galaxy looks like, this metric measures for how strong that bar is, and we can see it grow as it gets older. And using these metrics, we can define the time in which these bars were born and how strong they are. We can compare them between different galaxies. And this is for the bar itself. And we can find that over the age of TNG 50, so from effectively when the universe was born to now, which is about 13.8-ish billion years. In astrophysics, we can say giga-year, which is just billions. We see that these bars are born across the entire simulation. So bars are being born all the way from the early years of the universe to now. If we're looking for these peanut-shaped bulges, these 3 columns are the same galaxy, but at different times. This is kind of looking at the galaxy edge on. So we're looking at the bulge, trying to see if we can find those 4 spikes. But it starts off, they're not particularly there. We can't really see them. Then we can see them quite well defined. You can see the pinching in these lines here. And then by the end, they're still quite present. You can still see some pinchings, and we've got those 4 spikes there. Similar to the bar, we can measure this and give it kind of a quantitative value and measure when they formed, how strong they are. And you can see this as these kind of profiles. We can see these very nice, big, deep. They almost look like vampire teeth. And we can see these really deep minima here. This is where this peanut shape is at its strongest. So this galaxy grows this peanut very rapidly, and it weakens a little bit, but it's still there all towards the end. So how we're doing all these simulations, and we're finding the correct structures, and we're finding things that we find in the universe, but how does a simulation compare to what we actually observe in the real world? And that's one of the things that we did. So we compared TNG 50 to the Spitzer survey, which observed barred galaxies. And we were looking at how often do we find these peanut shapes in these barred galaxies in both Spitzer and in the simulation. This is a very complicated plot. Again, don't worry too much. I'm going to draw your attention to just 2 lines. The first line is this blue dot dash line, which goes all the way up here. And the second one is the yellow line. So the blue one is the real universe, is what we observe with Spitzer. And this bottom axis here is the galaxy's mass. So as we go from left to right, they're going to bigger and bigger and bigger galaxies. And what we find is that we find these peanut-shaped bulges more often in these very high mass galaxies. Actually, in all of the high mass galaxies, we find this peanut-shaped structure. If we compare that to TNG50, which is this yellow line, it doesn't all reach 100% of the galaxies at high mass. We kind of flatten off here, but there is a similarity. We do find this kind of increase from low mass to high mass, which is consistent between the universe and the simulation, which is an encouraging point because it means that we're starting to get the physics right in the simulation compared to the real world. But there is still something missing where our galaxies are not all forming these peanut shapes compared to what we find in the real universe. And that has something to do with just the technical limitations of the simulation. We haven't got infinite detail, we haven't got infinite resolution. And so there's a small aspect of the physics that we're missing that we just can't recreate with the computing power that we've got. Hopefully, as we start to develop and improve our technologies, we can start to understand what that kind of discrepancy is and then go closer and closer to simulating the real universe. For context, the Milky Way on this axis is about 10.7 in its stellar mass. So it sits about here. And if we were kind of at this point in both either Spitzer or TNG50, it would be very likely that the Milky Way would have this peanut-shaped bulge that we're interested in. And actually, observations do agree with that. We do find that the Milky Way has this kind of shaped bulge that we're interested in. So let's talk a little bit more about telescopes. So Spitzer is about a 0.85 meter mirror, and it is a space telescope as well. So it has the added benefit of being out of our atmosphere and being able to see high detail. And it also looks in the infrared, which is very challenging to do from the ground. So that's what gives it its detail to be able to study galaxies. Hubble, on the other hand, is a 2.4 meter mirror, so much significantly bigger. But the detectors on Hubble sit between the ultraviolet and the near infrared. So it looks at a slightly different area of the spectrum, which is good for different bits of science, but it's not good for observing very far distant galaxies. Now, we had these telescopes, and then very recently we launched and have been receiving images from JWST. Why is it so superior? Well, it's got a 6.6 meter mirror, so significantly larger than Hubble. And it does also observe further into the infrared, which this diagram will hopefully demonstrate for you. So we've got the left here, which is the Hubble Space Telescope. We can see the part of the electromagnetic spectrum that it observes in. So ultraviolet through the visible and slightly into the infrared. Spitzer on the other side goes much further into the mid and far infrared. So it's going to longer and longer wavelength. And that's beneficial for seeing through things like dust that appears in our galaxy. And when things are very far away in the early universe, they become what we call red-shifted. So their light, which may be predominantly in the visible range, gets shifted towards longer and longer wavelengths. And in the distant universe, they usually become into the infrared range. James Webb sits in this kind of middle range. So it goes from near to mid-infrared. But because of the benefits of its massive mirror, it sees much better resolution compared to the other two. So here's a quick example from a very recent paper. We have multiple columns here where we've got a JWST image, a Hubble image, JWST, Hubble, JWST, Hubble. But let's just compare two next to each other. So this is the Hubble Space Telescope image, which can see to very far distances. And we can start to see that it is a galaxy with a very bright central region with some spiral structure, but it's not particularly very well resolved. The equivalent JWST image, you can really see the spiral structure in very great detail. And this occurs in pretty much every case. We can see that JWST has superior resolution. We can start to see fine structure. And when we're trying to think about how bars were starting to form in some of these galaxies, this increase in resolution and this ability to define structures better removes some of the ambiguity between deciding whether we're going to classify a galaxy as barred or unbarred. If is it a spiral galaxy or is it an elliptical galaxy? The better the resolution we can get, the less confusion that we have in trying to do these classifications and our understanding of when these structures form in the real universe. A paper by Peter Irwin in 2018 demonstrated this for Spitzer directly, where we're looking at all the galaxies in their survey. And then this left panel is mass on the y-axis versus how far away the galaxy is. And we can see we've got some low mass galaxies nearby that we don't observe at very large distances. And this isn't because there is no low mass galaxies at these great distances. It's purely because the telescope itself can't detect them because they're too small for the telescope to resolve. On this right panel, we have a similar story. So as a function of distance, this is the size of the bar. So this R25 is the size of the bars in these galaxies. And you can see there's almost like an artificial lower limit here. And that is just purely the limiting power of the telescope. It can't observe any smaller objects at these distances. So our understanding of the real universe of when these structures form or how far away they can form is limited by the technology of its time. When we're starting to introduce JWST images, these are slowly coming through, and as they're starting to be analyzed, our understanding of when these structures form is shifting slightly. So this is the bar fraction, so the number of galaxies that have bars in them as a function of redshift. Redshift is just another way of measuring effectively distance or how far back in time we are going. These purple points are from the Hubble Space Telescope, and these kind of bluey-green points here are from JWST. And you can see, especially this data point here, which is starting to get the most interesting, that they're agreeing somewhat in kind of their averages, but JWST are starting to stretch how far back we're starting to observe these bars. And we are finding bars at further and further back time. So the further back in redshift that we are, so the higher is this number, the younger the universe was. Now, when these results started to come out, a whole bunch of magazines and websites were starting to have headlines like this. So after 2 years in space, the James Webb Telescope has broken cosmology. It's like, it's broken, can we fix it? Did James Webb Telescope images break the universe? JWST is probably using early galaxies bend astrophysics. Now, of course, magazines were going to exaggerate their titles a little bit, but how far has JWST challenged our understanding? This paper came out last year, which was one of the most kind of interesting kind of outputs of JWST, especially in galaxy formation and evolution. And they found a Milky Way-like barred spiral galaxy of redshift of 3. Now, that doesn't sound like overly exciting because this is a paper title, but for astronomers, this was like redshift of 3, what is going on? And this was the images that it produced. And going back to my earlier images or attempted images of the night sky, this is very much another kind of smudge. And you kind of have to squint and go, okay, what are we actually seeing? And we are starting to see certainly a galaxy, the startings of some level of kind of spiraling structure coming from the center. It's elongated in the center, which would be bar-like. Would we classify this as a bar? It's potential. It's a weak bar, and this might be the beginnings of what would grow to be a Milky Way-like galaxy. So it's certainly interesting, and it's certainly pushing the edge of what we thought was kind of possible at looking at this very early period of the universe. But has it broken cosmology? Well, thinking back to TNG 50, when we were studying when these bars form, and we were looking at how far back we go, on this top axis here, I've got Z form, or the redshift at which the bar formed in TNG 50 that we measured. And this line here is redshift 3. And this turning point here shows that there were bars being formed in the regime between kind of redshift 2 and 3. So TNG 50 is actually saying potentially we could have bars that are that old. And this is not breaking cosmology. TNG 50 was built on our current models of cosmology and our current understanding of how the universe works. And TNG 50 is agreeing that actually stuff could form that early. In other studies, so the same one that kind of presented this results also showed this similar thing. So this yellow star is this very early galaxy. They've named it SEERS 2112. Very imaginative, but that's just the survey number. And what they did is they looked in TNG 50 and looked at galaxies that look like the Milky Way at the end of the simulation and turned back the clock all the way back to redshift 3, which is this kind of red shaded region and this dashed line here. And SEERS sits right in that regime. So TNG 50 essentially says we can have galaxies that are of that size that could potentially form a bar. So we have unbroken cosmology, thankfully. It is starting to probe the very edges of our understanding because a lot of this was kind of theoretical predictions, and now we're starting to take measurements that match our predictions, which is always exciting. So this is the kind of the next generation. We've got JWST, we've got huge simulations like illustrious TNG. The question then becomes is, sorry to push this analogy a bit too far, what is the Deep Space Nine of simulations and telescopes? On the simulations front, there's no formal kind of next project yet, but no doubt there will be one announced soon, which will be super exciting. On the telescope front, however, it is a really exciting time to be an astronomer. To have a true successor to Hubble Space Telescope, NASA are launching the Nancy Grace Roman Telescope. This is a great piece of machinery that's coming. It's got the same resolution, so the same ability to measure detail in the sky, but it's got a field of view 100 times larger than Hubble. So for the same image with Nancy Grace Roman, you'd have to have 100 observations of Hubble to be able to do that. And it's about time. Hubble has lasted over 30 years, way beyond its planned operational time. And this will be the replacement telescope that will really bring a new life to kind of the UV, visible, and infrared kind of ends of the spectrum. Another great telescope that's being built, which is not too far away from being commissioned, actually, it's only in the next couple of years that we should have first light and survey operations going, is the Vera Rubin Observatory. Now, the Vera Rubin Observatory is being built in Chile, top of a mountain. It's a very, very wide field of view telescope, and it's going to image the entire southern sky every 3 nights. So it's just going to do a survey constantly every clear night it has, which on the top of a mountain in Chile, they get a lot more than us in Lancashire for sure. And this will be serving the entire sky. So it'll be trying to understand both the distant universe in terms of all the galaxies it's going to observe, as well as Milky Way science, and also solar system science as well. This is going to be tracking solar system objects and those pesky Starlink satellites. I know this is going on YouTube, so I may have inadvertently got you in trouble there. I do apologize if I do. But this will no doubt be detecting those every single night. Another project is the Giant Magellan Telescope. Can't remember where this one's being built, but this is another very large facility that's coming our way. And then we've got the European Extremely Large Telescope. Again, astronomers are not known for their naming conventions. We already have the Very Large Telescope, and this is now the Extremely Large Telescope. But this is a European Southern Observatory Telescope, which is already under construction. Most of the base and the foundation work is underway. And this is going to be another ground-based facility that's going to do some really deep and interesting science. So I have taught for a fairly long time and very many different topics, but thank you for indulging me, and hopefully I've given you some takeaways about galaxy formation there. So thank you very much.
Stephen, thank you very much. We're going to move on quickly to questions and answers. Can I ask you to stop sharing your screen so I can see the rest of the meeting? And could I ask somebody in the room if they would turn on some lights, please? Just one by at the back, preferably. Thank you. So, what a fascinating talk. And I'd like to claim the bonus points. It was Stargate SG1. So, questions, please. As usual, if you're digital, can you put up a digital hand? If you're in the room, somebody's been throwing money around already this evening, so throw it in my direction. In the room, starting off with Mike Scholar.
Good evening, Steve. You showed a picture showing dark energy expansion. Is this expansion accelerating, or is it a steady acceleration? Is it exponentially increasing?
That is a very good question, and unfortunately, I do not know the current accepted value for. Whoops. sorry, I lost my screen for a second there. Accepted value, I believe it is accelerating at whether it's a linear exponential or what kind of function that is, I'm not entirely sure, but I believe the expansion is accelerating.
Big rate of certainty now.
I believe so, yeah. I believe that's kind of the current accepted way we're going, is that it is expanding at an increasing rate.
Thank you.
Okay, from our American correspondent, Greg McNiff online. Evening, Greg.
Thank you very much. That was a great talk. I have a question about machine learning because I actually heard a lecture like a week ago, and the question is really, I know we have an evolution in the telescope, and particularly with, I think, Europa and the Baron Dunn Observatory. But I wonder, do you think we have the data now that machine learning is able to give us more insight, or do we need more data? And what I'm trying to ask is, like, it feels like machine learning is really becoming a valuable part of these discoveries, and it's just a question of getting it the data. And I'm curious how you think about it as a tool going forward.
Yeah, with many things, scientists always complain about more data, so I imagine the machine learning does as well. The more data you can feed it, hopefully the more insights it can give you. I think like the example that I gave about Zooniverse and Galaxy Zoo progressing, I think is one of the great positives of and the great use cases of machine learning. Because what we started with a bunch of citizen scientists doing the legwork of classifying and labeling data. And then we got a great data set to do science, but we also had a great training data for machine learning. And then what happens is machine learning can take over the heavy lifting of the general easy to cases. What machine learning is really good at is going, I've seen 10,000 of those. Here's a new one. I know very well that this is something that I know really well, and I can say with confidence, that's what it is. Then you throw it a curveball, then you throw it an unusual image, an unusual piece of data where you go, the machine learning goes, I really don't know what that is. And it can't, in some cases, it might give you a suggestion of what it could be, but what will really then be useful is that actually you hand that weird piece of data back to a scientist, back to someone to put eyes on it, who will then be able to get a better understanding of it. So machine learning is doing a really good job of doing the easy kind of heavy lifting cases, where we've got a new survey telescope and it's observed 1,000 new objects. Machine learning can sort through that and go, I know what all those are, and leave you behind the really interesting stuff. So for galaxies, if it's just another kind of grand design spiral, the machine learning will go, that's a grand design spiral. You don't really need to go much further than that. But then we found objects like these green P galaxies, which is one example that comes to mind, which were an unusual case that the machine learning was going like, I don't know what to do with this. And the citizens and scientists started to group together, and now we've got a new classification of objects. So as a tool, machine learning is great for when we've got very large data sets to very quickly sort through stuff that's interesting and stuff that's still potentially interesting, but is very easily classifiable. And I see that as one of the big use cases for it.
Perfect. I just had a follow-up on the impact or the influence of black holes in galaxy formation. It feels like there's been some debate on the timing. I guess I'm going back to the Big Bang, or certainly the Milky Way, like chicken and egg. What came first, the galaxy or the black hole? And I'm not an astrophysicist or remotely knowledgeable, but could you just weigh in on that for 30 seconds?
Of course, yeah. So I've neglected black holes really throughout the talk, because when it comes to kind of the dynamics of galaxies, unless we're talking about what we call active galactic nuclei, which are ones where they've got black holes with stuff falling actually into them, which forms these jets and blows some of the gas out of the galaxy, the actual mass of a black hole compared to the entire galaxy itself, if you include the stars, the dark matter, and the gas, is actually quite small. So a lot of the time when we're doing these simulations, a good few of them will include black holes for other interesting physics. But actually, when you're trying to form a spiral galaxy, if you neglect the black hole, they can still form. They're not really that kind of like linchpin in galaxy formation. They still provide some other kind of interesting effects in physics, but to form a spiral galaxy, it doesn't really care if it's got a black hole in its center or not.
Perfect. Thank you very much for the talk.
Thank you.
Any more questions in the room? No? Nobody
I'll
else?
ask a question.
Yes.
Hi, Stephen. I've got a slightly easier question for you, I think. I was just interested in how you actually got into studying like galactic formation. Maybe just like how was it anything in your master's topic that got you interested in it, or anything before that?
The journey actually started in undergraduate. I was quite fortunate in that one of the professors at the University of Central Lancashire, eventually my supervisor, he taught a kind of computational scientific computing module on the undergraduate course. And I was like, I really enjoy computers. I really enjoy like working in analysis in this way. And part of his research is these simulations. So I was able to do space and science from a laptop, doing computing, and I was dealing with really big data sets, and that kind of snowballed into using kind of simulations for astrophysics. And galaxies and galaxy simulations were kind of a natural follow-on from that. So that started in undergraduate, and I did my undergraduate project in the orbits of stars in a galaxy, and then master's and PhD followed on from there. So yeah, it was a love of kind of computational astrophysics that really put the foot in the door, and then galaxies were just they're really cool objects, and I really enjoyed the study of being able to turn back the clock on billions of years. These processes happen over such a long time scale that I wanted to see it almost in fast forward, and these simulations allow you to kind of really get into the process of doing that.
Okay. Thanks for that. Peter Lloyd.
Yeah, thank you. Very interesting talk. Can I take you back to an early slide you showed? Now, what I like to think of as modern scientific mythology says that the universe popped into existence some 13,700 million years ago. Where does that number come from? Can you tell me?
The 13.8 billion years? Yes. So that actually comes from Hubble as well, looking at kind of the rate of expansion of the universe. So it comes from the Hubble constant.
It's reciprocal of the Hubble constant.
Indeed, yes.
Well, if you look at that diagram you have that looks a bit like a bell,
yes,
the reciprocal of the Hubble constant will be the slope of the top edge of that. Then you've got inflation, which implies that the age of the universe is considerably less than the reciprocal of the Hubble constant.
Potentially, yes. And then also there is the unfortunate consequence of measuring the Hubble constant where we are in the universe. Because where we are may be in one of these weird void regions, or we may be in an slightly dense region. So as we're trying to estimate this, it does become a challenge, yes. And the current problem is actually there's two prongs of of measurements that are settling down into two slightly different values of the Hubble constant. And the problem is the errors are starting to shrink to the point where they're disagreeing with each other. If the errors are large enough, they're in agreement. But when they start to shrink too far, we've now got two very precise measurements of two different numbers. So yes, 13.8 is the current kind of accepted value, but I very much concede your point that it is very tricky to calculate this.
But can one estimate, how can I put this, the ratio of the size of the universe when inflation stopped and the size it is now? Is that increase during inflation a major part of the present size, or is it a very tiny part of it?
I believe the graphic I may have used may have exaggerated the kind of the break between kind of inflation then and now.
That's what I felt.
Yes. So yes, you may be right. Yes. And so in fact, yeah, the Hubble constant may not necessarily be constant.
Oh, I appreciate it being constant, but it sort of gives you a rough idea. Yes.
Indeed, yeah. That was unfortunately the best graphic I could find to show that.
It is the usual one.
Indeed.
I accept that. Well, thank you very much.
No problem.
I'm looking for questions in the room. Well, they're very quiet in the room tonight. I think telling them off at the start of the meeting has worked. And Peter Lloyd wants to come back for a second round.
Oh.
Peter.
Yeah, sorry, can I come back? Because another question I was going to ask you, and now I've forgotten what it was again. I'm like this. Sorry, Paul. I forgot.
Well, I'll ask a question.
It'll come back to me as soon as you go off and talk to somebody else. Sorry about that.
I might have missed it because I was busy doing something with meeting entries and things at the time, but could you just tease out a little bit why bars form in spiral galaxies?
Oof, that is potentially another bit of a talk in of itself. But to put it very introductorily, when you've got a nice disk galaxy and it's wanting to spin, you get instabilities in the disk. So the disk isn't perfectly flat, and it's not perfectly uniform in dense. So when you get these kind of mismatches in density, the disk starts to wobble and flex, and you get instabilities, which is why you start to get spirals. And then these spirals have a feedback mechanism that as they go towards the center, they like to straighten out and they like to form these very straight rotating structures. And that's what we call the bar. So when you start to get spirals, you start to get this, what we call the bar instability, and where these spirals, instead of curling round, they straighten out and they form this bar rotating. So yeah, it's a natural consequence of when you've got a spinning disk.
So does every spiral galaxy then end up having a bar, or are there other factors like size, etc., that will?
Yeah, so mass, the thickness of the disk, and different distributions of density can all inhibit bar formation, but they actually are quite a common consequence of kind of spiral structure. So we do find bars very commonly. So the Milky Way is not necessarily so unique in many ways. Of the Milky Way's size, most galaxies like the Milky Way have bars and have spirals.
Right, thank you for that. Mick Nichols, online.
Yeah. With all these new telescopes that are getting developed and the new space telescopes that are getting developed, as they're getting more powerful, do you think we'll ever get back to the get an image or the discovery or something where we can actually get back to the point of the Big Bang itself and actually see it?
Well, the furthest back we can go is the cosmic microwave background, because as you go to longer and longer wavelengths, you are looking further and further back. So the cosmic microwave background is effectively kind of one of the deepest pictures we can take. JWST is pushing us to those kind of limits. I'm trying to think if there's going to be another one that'll go much any further than that. I don't think in more recent years it's going to go. JWST is going to be the deepest we're going to go for a while. The problem then becomes, coming back almost to this inflation problem, is has the universe expanded larger than actually we can see back? Because the universe has to be so old for the light to be able to reach us in the first place, because light travels at the speed of light. So if the universe is only 13.8 billion years old with current accepted value, we can only see that far back. But the universe may be bigger than how far light may have been able to travel to be able to get to us. That is one of the challenges, and that is the challenge of cosmology is trying to understand this problem. And that is kind of at the edge of my knowledge. I prefer galaxies. Cosmology is a bigger picture, but hopefully that is as satisfying of an answer as you can get. We will reach a potential limit of how far we can see purely just because of how far light has even traveled.
Thank you.
Okay. And I can't see any questions online. I've just got one more question. Oh, Peter's going to come in, but I'll ask my question first if you don't mind. Peter, globular clusters.
Yep.
What are they?
So
why have we got them?
Why have we got them is I think a bit more of a philosophical question. Globular clusters are structures within a galaxy, and that typically means you've got quite a large gas cloud that has collapsed and a whole bunch of stars have formed all at the same time. Excuse me, sorry, usually quite in close proximity. So the Milky Way has quite a few globular clusters where you've got a whole bunch of stars that formed all at the same time quite compactly. So there is a blurred line between some of the very largest globular clusters that we've discovered and some of the very smallest galaxies that we've found. And that is another area of research where we've got these kind of extragalactic globular clusters that are what we call ultra compact dwarfs. So dwarf galaxies that are very, very close together. And the origin of them is a whole field of research as well.
Okay, I think there's a third talk there, Stephen. And I'm going to come back one last time to Peter Lloyd, who's remembered his question, I hope.
Yeah, I'm sorry, Stephen. Yes, I've remembered the question I was going to ask you. Did you say that dark matter formed before normal matter?
Yes. So the universe is comprised of mostly dark matter and a smaller fraction of normal matter. And it was all in the energy creation of the universe. There was matter and dark matter kind of all at the same time, but normal matter was in the form of energy. It wasn't formed of kind of solid particles yet. But dark matter was able to start to clump together under gravity, under the kind of first inflationary period. So it was all there at the beginning, but dark matter not interacting with light, only interacting with gravity, is able to collapse and form these structures.
So dark matter can form at very high temperatures.
Yes, yeah, so effectively because when we think about temperature and we think about energy, we can think about the electromagnetic spectrum. So in terms of heat, that's infrared. In terms of like visible, that's visible photons and such. So when matter is pure energy, it exists only as photons of light, effectively. Right. And they both formed at the same time with matter and dark matter. But dark matter doesn't interact with light, or else we would be able to see it. It only interacts with gravity. That's why we call it dark, because we can't see it with light. It doesn't interact with the electromagnetic spectrum in any way. It just interacts with gravity. So we can see the.
But it formed the instant of the Big Bang.
Yes, effectively, and we can see the influence of dark matter through gravitational lensing, and why we see the large scale structure of the universe that we do. We know it's there. It just doesn't interact with light directly, so we can't image it. We can't scan for it. We can't pass anything through it.
Okay, well, thank you, and thank you, Paul, for letting me come back.
Yeah, I'm going to make this the last question because I think we've worked Stephen hard enough. We'll go back to Greg. Greg, question, please.
Yeah, thank you. Just on that point, do we know the existence of dark matter from gravitational lensing and the rotation of the Milky Way galaxy, or how do we know dark matter exists?
Well, not just from the rotation of the Milky Way galaxy, the rotation of pretty much every galaxy. Different galaxies have different proportions of normal matter to dark matter, but if you don't account for the dark matter, the rotation of those galaxies don't really make sense, and actually they'd start to fling themselves apart because there's missing extra mass in those kind of rotations. And that's what Vera Rubin actually started to measure and discover, which is why we named the observatory after her, is that she was the one that kind of showed that these rotation curves need dark matter to kind of account for it. And there was another part of your question was gravitational lensing. Yes. In a similar sort of vein is that when we're looking at these distant galaxies, especially some very nice ones from JWST, because of the resolution, you can really see kind of some of these like twisty and weird galaxy shapes. That is dark matter between us and the light of that galaxy reaching us that's not accounted for in normal matter. Because if there was normal matter in the way, it would either be emitting light or it would be absorbing some of that light, and would get in the way and we wouldn't be able to see it. So this is something that's warping space and changing the gravity of space and bending that light round a heavy mass, but without interacting with that light to either block it or to add to it. So this is kind of another kind of positive prediction for dark matter, is that we can see its effects throughout the universe, but we know it's still not interacting with light.
Perfect. Thank you.
Okay, ladies and gentlemen, I think we owe Dr. Steven Gough-Kelly a huge vote of thanks. So will you join me in giving a big next sprint to International Society? Thank you. Thank you very much.